and specifically the ones that we can calculate for in conservation of energy. So, there are three basic types that we're going to calculate for. Translational kinetic energy means energy of a translating object, and for instance, if I have a star, but we have a nice object to translate, this, this is an example of translating, this is an example of translating, and this is an example of rotating, which is not translating. So as long as it is moving side to side or up and down, that is translating, and this is rotating, so changing the orientation of an object. We can also have rotational kinetic energy, which means how fast it's spinning, and we will not be calculating for rotating, but it is something that can be done in more advanced classes. Gravitational potential energy, which is due to elevation above the surface of the Earth, so how strongly it's pulled back to the surface of the Earth by the force of gravity. Or elastic potential energy if you have something stretchy, like a rubber band or a spring. Now, if we look at the formulas for these, for translational kinetic energy, it is just 1/2 times the mass times the speed squared. The nice thing about energy is a scalar quantity, so we don't have to worry about positives and negatives. Everything is positive. Gravitational potential energy, as you would expect, depends on acceleration of gravity, the mass of the object, and the height above the Earth's surface. And elastic potential energy, of course, deals with stretchy things. So here is our Hooke's law constant, K, stretchiness, X, which is displacement, so how much the object is stretched, which is squared times 1/2, and that's potential. Now, to solve conservation of energy problems, we have to think about each of these terms before and compared to an after. So we have three questions we ask ourselves. Is it moving? If it's not moving, translational kinetic energy is 0. Is it elevated? Which means above whatever height we're saying is 0. If it's not elevated, this term is 0. And is it stretched? And if it's not stretched, then this term is also 0. We ask the same three questions again afterward, and we use a prime to show that these are terms afterward, and nothing over here to show that they're terms before. So let's do an example. This example can be solved very easily with our previous calculations, but I want you to show you how it can be calculated with energy equations. It says a large chunk of ice has a mass of 9.5 kilograms, falls from a roof that is 15 meters above the ground. Ignoring air resistance, calculate the speed of the ice as it hits the ground. So, we have the roof on a very wobbly house, and we have a chunk of ice teetering on the edge of the roof, and it falls down like so. And let's look at the information we have. Mass is 9.5 kilograms, and the height of the roof is 15 meters above the ground, and we would like to know how fast it hits the ground. So this is what we know, and this is what we want to know, actually, so we wrote it all over here. Let's think about our energy equation. We had kinetic energy translational plus potential energy gravitational plus potential energy elastic equals the same three terms after the ice falls. So we have ice teetering on the edge of the roof, ice hitting the ground, and we're comparing those two situations. Let's find out what 0 first. First of all, there's nothing stretchy at all involved in this problem. So we'll cross out elastic right away. When it's teetering on the edge, about to fall, it has a velocity of 0. So that term is 0. Because there's a v in there and v is 0. When it hits the ground, its elevation is now 0. So that term is 0. Well, what do you know? That reduces to a fairly simple situation. And to put in our expressions, gravitational potential energy is mgh equals, because that's all that's left on the left, 1/2 mv squared on the right. And I can simplify a little more because I can cross out my m. And now let's see what we have. Remember, this is all scalar, so we put 9.8 in as a positive. The height is 15 meters. Those units are all compatible. 1/2 v squared. So if I put that in the calculator, I get, I get 17 meters per second. And that is the speed at which the ice hits the ground. So let's try a problem with something stretchy. Alright. A zookeeper pulls back her bow to shoot a tranquilizing arrow into a sick animal. This diagram is going to be a little bit more difficult. She pulls the bow back 15 centimeters from equilibrium, and the arrow leaves the bow with a speed of 35 meters per second. What is the spring constant of her bow? Alright, let's see what we can do here with this diagram. Where's the bow? Tranquilizing arrow, of course, because no animals were harmed in this problem. And let's see, what do we know? We know that stretch or displacement is 15 centimeters, and we want that to be compatible with our other units, so 0.15 meters. We know that the velocity afterward is 35 meters per second. Notice how I put a prime to indicate it's after. And we want to know k. Alright, let's lay out our equation and see what we got. So kinetic energy translational plus potential energy gravitational plus potential energy elastic equals same 3 prime for after okay. And let's figure out what's 0. There are stretchy things involved. It's stretched here, but it's not stretched afterward, so that's 0. Because here, x is equal to 0. There is no change in height, so height, if we set 0 height where we're starting, it's 0 height afterward, so there's no change in height. It is not moving before we shoot the arrow, but it is moving after we shoot the arrow. And again, that simplifies us to a pretty decent equation. So we have 1/2 kx squared before equals 1/2 mv squared afterward. And you'll notice that the 1/2's cancel. This helps us a little bit with algebra. And we get kx squared equals mv squared. Oh, we need to know the mass of the bow, or the mass of the arrow. So let's say the mass of our arrow was, arrows are not very heavy, say 10 grams, which would be 0.01 kilograms for the mass of our arrow. Alright, now we can keep going. K times stretch in meters, so our units are compatible, 0.15 squared equals mass 0.01 kilograms times speed, we do know speed, 35 squared. So when I put that in the calculator, we get, just to simplify one more step, K equals 0.01 times 35 squared divided by 0.15 squared. Be careful of your order of operations when you do this. And that gives you, oops, forgot again. That gives you 544.4, and K is in units of newtons per meter. And that's how we solve an energy problem.